Welcome to this video about how we can use the logistic regression model as a binary classifier to, for example, predict if someone has a disease. Suppose we have the following data. Note that this is just fictive data where the values have been selected for the purpose of this video. The variable on the y-axis represents if someone has prostate cancer or not. For example, these 7 individuals have prostate cancer, whereas these 7 healthy controls do not have prostate cancer. Note that the ones in the healthy control group are denoted as being healthy, whereas the individuals with prostate cancer are here simply called cancer patients. For example, this person has prostate cancer and a prostate-specific antigen level of about 3.8, whereas this person has a PSA level of about 2.5 and is known to be healthy. Let's change the labels on the y-axis so that yes is coded as 1 and no is coded as 0. From the basic lecture about logistic regression, we know that the following logistic function can be fitted to the data. If you use the statistical software to fit the logistic regression model to the data, the parameter B0 is estimated to minus 5.75, whereas B1 is estimated to 2.75. Let's plug in these estimated parameters in the equation. If you now change the PSA concentration from 0 to 5 and calculate the probability for a range of different PSA values, we can draw the following S-shaped curve in the plot. We will now see how well our logistic regression model can classify if the individuals have prostate cancer or not. We first need to decide a cutoff or threshold value that we like to use in order to determine if someone has prostate cancer or not. A common cutoff value to use in logistic regression is the value 0.5. It is a reasonable cutoff value to use because if the probability that someone has prostate cancer is greater than 50%, we would predict that the person has prostate cancer. And if someone has a probability less than 50%, we would predict that the person does not have prostate cancer. For example, let's see what the model predicts for this person, which in this case is known to be healthy. If we draw a vertical arrow from the point to the curve, and then a horizontal line from the curve to the y-axis, we see that the value of the y-axis where the line intercepts is about 0.7. To get a more exact estimate of the probability, we can use our previous equation with the estimated parameters. If we plug in the PSA level 2.5 for this person in the equation, we see that the model predicts that the probability that this person has prostate cancer is 75%. Since 0.75 is greater than the cutoff value of 0.5, the model predicts that this person has prostate cancer. This is an incorrect prediction because we know that the person is healthy. We would therefore call this a false positive result. In contrast, the model will predict that this person with a PSA level of 2.0 has a probability of 44% to have prostate cancer. Since 44% is less than the cutoff value, the model will predict that this person is healthy. Since we know that this person is healthy, this is called a true negative result because it is true that the person is healthy. If we let the model predict the class of the following person, with a PSA level of 1.6, we see that the estimated probability is 21%. Since this is less than 0.5, the model predicts that this person is healthy. This would be called a false negative result, because this person, that we know has prostate cancer is incorrectly predicted to be healthy. Recall that this equation can be used to calculate a certain probability for a given PSA level. If we solve this equation for the PSA variable, we can calculate the value of PSA for a given probability to have prostate cancer, which is here denoted by P. We would now like to calculate the corresponding PSA level for a cutoff value of 0.5 based on estimated values for B0 and B1. We see that the corresponding PSA level for a cutoff value of 0.5 is 2.09. Let's add a vertical line at 2.09. All individuals represented by the data points to the left-hand side of this line will therefore be classified as being healthy. Where data points in this rectangle are false negatives, because these individuals are classified as being healthy even though they are known to have prostate cancer. In contrast, individuals represented by the data points in this rectangle are true negatives, because the model predicts that these individuals are healthy, which is true since they come from the healthy control group. All individuals associated with the data points to the right-hand side of this line are classified as having prostate cancer. Data points in this rectangle represent true positive results, because the individuals are correctly predicted to have prostate cancer. Whereas data points in this rectangle represent false positives, because it is false that they have prostate cancer. Instead of viewing the graph for how to classify, a simpler way is to calculate the probabilities for each of the individuals. These are the PSA levels of the 14 individuals. In total, we have 7 patients with prostate cancer and 7 healthy controls. For example, this person has prostate cancer and a PSA level of 2.1, whereas this person is a healthy person with a PSA level of 2.5. Let's calculate the probabilities according to the logistic regression model that the individuals have prostate cancer given their PSA levels. For example, if we plug in a PSA level of 2.1 in this equation with the estimated parameter values, we see that the model predicts that this person has a probability of about 50% to have prostate cancer. Let's calculate the probabilities for all 14 individuals. Based on these probabilities, we can now predict if someone is healthy or have prostate cancer. We would predict that these have prostate cancer because they have a probability greater than the cutoff value 0.5. Since we know that these individuals have prostate cancer, we know that these are correctly predicted. Whereas this person with prostate cancer is incorrectly predicted to be healthy. Remember from the lecture about sensitivity and specificity that the sensitivity is a measure of how often the test shows a positive result out of the ones who actually have the disease. We see that we have 6 true positives and 1 false negative. 6 out of the 7 patients with prostate cancer are therefore correctly predicted to have prostate cancer, which gives us a sensitivity of 86%. We'll now calculate the specificity. Remember that the specificity is how often the test shows a negative result out of the ones who do not have the disease. The healthy controls represent people with no disease. We see that we have 6 true negatives and 1 false positive. Since 6 out of the 7 healthy individuals are classified as being healthy, the specificity is here equal to about 86%. We can also calculate the accuracy, which is the number of correct predictions divided by the total number of predictions. We see that 12 out of the 14 predictions are correct, which gives us an accuracy of about 86%. So far, we have used the cutoff value of 0.5. However, if we like to increase, for example, the sensitivity, we could reduce the cutoff value. For example, let's reduce the cutoff value to 0.2 to see if we can increase the sensitivity. Note that the probabilities are still the same because we have just changed the cutoff value, not the estimated parameter values of the model. By using a cutoff value of 0.2, these 10 individuals will be predicted to have prostate cancer because they have a probability value greater than 0.2. Whereas these are predicted to be healthy because they have a probability value less than 0.2. Since all the patients with prostate cancer are now correctly predicted to have cancer, the sensitivity is 100%. However, since only 4 out of the 7 healthy controls will be predicted to be healthy, the specificity is now only 57%. Since we make in total 11 correct predictions out of 14, the accuracy has been reduced from 86% to about 79%. Graphically, we can visualize the classification with a cutoff value of 0.2 by placing a vertical line at about 1.59 and classify the points like this. We see that with this low cutoff value, we have 7 true positives and no false negatives, and 4 true negatives and 3 false positives. If we try many different cutoff values, we can create the ROC curve. By using a very low cutoff value, all individuals will be predicted to have prostate cancer, which results in 100% sensitivity and 0% specificity. If we increase the cutoff value a bit, one of the healthy individuals is now correctly predicted to be healthy, which increases the specificity from 0% to about 14%. We continue to increase the cutoff. Watch the lecture about ROC curves for a more detailed explanation. If we continue like this, where we try all possible cutoff values, we will get the following ROC curve. Note that the cutoff values behind the points in the ROC curve now represent probabilities generated by the logistic model. For example, if we use a cutoff value of 0.47, we'll get a sensitivity and specificity of about 86%. And if we use a cutoff value of 0.23, we'll get a sensitivity of 86% and a specificity of about 57%. And if we use a cutoff value of 0.8, we'll get 71% sensitivity and 100% specificity. We will now briefly discuss how we can validate our model with the same techniques as we covered in the video about validation. For example, we could divide the data into a training dataset and a test dataset. We then fit the logistic regression model to the data, which means that we estimate the parameters of the model so that the model fits as good as possible to the data. Then we decide an appropriate cutoff value depending on if we think that the sensitivity or specificity is more important. In this example, we set the cutoff value to 0.5. Then we remove the training dataset and add the test data to see how well the model predicts on new data. We then use the model to calculate the probability that the individuals in the test dataset have prostate cancer. Based on these probabilities, we can calculate the metrics such as the sensitivity and specificity based on the test data. Watch the lecture about validation to see how we can use different types of validation techniques. Note that we have up till now only used one variable in our logistic regression model. Although we can compute the corresponding probabilities for the given PSA levels, the full power of logistic regression has not yet been shown. We have basically so far only computed the probabilities based on the PSA values. This does not improve the sensitivity or specificity of the PSA test. We would have got the same RC curve and accuracy by using a simple cutoff value based directly on the PSA values. Watch the lecture about the RC curve to see how we can compute the RC curve by using just a simple cutoff value. For example, if we use a cutoff value of 2.09, we'll get the sensitivity and specificity of about 86%, which is the same value as we got when we used logistic regression and a cutoff value of 0.47. We'll now see how we can combine biomarkers with logistic regression by using more than one explanatory variable. We'll here try logistic regression on the same dataset as we used with the linear discriminant analysis. This dataset consists of 2 explanatory variables instead of just one. However, note that this dataset is quite small to fit the purpose of this video. Remember that the more data we have, the better predictions we'll make. This dataset consists of measurements on the C-reactive protein in blood and the body temperature of 12 patients who had entered the hospital. Once the patients had entered the hospital, the presence of bacteria and virus were analyzed from different samples. However, it usually takes several hours or days to determine if a patient has a viral infection or a bacterial infection. After 2 days at the hospital, these patients were found to have a viral infection, whereas these 6 patients were confirmed to have a bacterial infection. Since antibiotics are only effective on bacteria, only these patients were treated with antibiotics. The problem is that we have to wait about 2 days to know if antibiotic treatment is appropriate or not. It would be great if we can use the CRP concentration or the body temperature to tell if a patient has a bacterial or viral infection, because the measurements of these variables can be done with just an hour. If we plot the CRP concentration of the 12 patients, we see that the ones with a viral infection generally have a lower concentration of the CRP compared to the ones who have a bacterial infection. However, the problem is that no simple cutoff line can separate the groups very well. The same is also true for the body temperature, because we cannot separate the patients with bacterial infection from the patients with viral infection by using only the body temperature. However, if we plot the CRP concentration and the body temperature in the same plot and use different colors for patients with a viral infection and bacterial infection, we see that the following line can separate the 2 groups completely. This indicates that logistic regression can separate the 2 groups if it uses both variables instead of just one of the variables. We could use the following model where we like to predict the type of infection based on the explanatory variables CRP and body temperature. Once we have fitted the model to the data, we can use the following equation with the estimated parameter values to calculate the probability that a person has a bacterial infection. With this equation, we can calculate these probabilities. Since the model generates a perfect separation between the 2 groups, the probabilities are very close to 1 or 0 and have therefore been rounded to ones or zeros. We see that all individuals that have a viral infection have a probability close to 0 to have a bacterial infection. These individuals are therefore correctly classified as having a viral infection. All the individuals that have a bacterial infection are correctly predicted since their probability of having bacterial infection is close to 1. In other words, these probabilities are greater than 0.5. However, when logistic regression generates a perfect separation between the groups, like in this example, there is a large uncertainty in the estimated parameter values. This is due to that a lot of different shapes of the logistic function are possible in order to generate perfect separation between the groups. This results in large confidence intervals and high p-values of the estimated parameters, although the model makes a good job as a classifier. One nice thing with logistic regression is that we can use many explanatory variables to make better predictions. We can also compare models to identify the best model with relatively few variables that still predicts well. For example, if we try a model with 7 variables to predict if someone has a viral or bacterial infection, we might come to the conclusion that this simple model does not predict significantly worse than the full model with 7 variables, which suggests that the simple model with only CRP and PCT is enough to classify the individuals. Once we have fitted the model and done some validation, we can use it for prediction in real-life situations. Let's say that we have fitted a logistic regression model on some data collected on patients with known infection, and that the following parameter values were estimated based on that data. We can then use the following model to estimate the probability that someone has a bacterial infection. Suppose we like to use this model to predict if a person with a CRP level of 75 and a PCT level of 80 has a bacterial infection. We plug in the CRP and PCT levels in the equation and calculate the probability to about 0.9. If the threshold for having a bacterial infection is set to 0.5, we would predict that this person has a bacterial infection. Let's take another example. If the CRP and PCT levels are 58 and 66, the predicted probability for a bacterial infection is 26%, which is less than the cutoff value. The person is therefore predicted not to have a bacterial infection. Note that using the model for prediction depends on how common the disease is, the prevalence. In our previous example about the PSA levels, we had a prevalence of 0.5 because we selected 7 healthy controls and 7 prostate cancer patients. However, if we would have a lot more individuals that are healthy, which is what is expected if we use the PSA test in the population where the prevalence is less than 50%, then the curve will be shifted to the right like this. This is due to that the model then fits better to the majority of the data points. The corresponding PSA cutoff value that gives 50% probability that you have prostate cancer has now increased from about 2 to about 3. It is therefore important that we think about the prevalence when we interpret the predicted probabilities. This was the end of this lecture about using logistic regression as a classifier.